Okay, in this video we're going to be talking about the different phases in structural analysis and design. So basically we're going to talk about the procedure of analysis and design in terms of structure. Okay, so let's say that there are two main factors in this entire process, and that is the analysis and the design. So both of them have some inputs and also some outputs. So analysis has some inputs which are applied loads, material properties, and geometry. So let's say that you're going to do a structural design for an building structure. Okay, so you receive the plans for that building structure. Let's say let me just take a pen. Let's say that you got a plan for that building structure. This is that building. Here's a room. There's another room here. There's something there. Okay, and then you have to support this particular building structure. So to support this particular building structure, you're going to put in a frame structure, right? So let's say you're going to put in a frame structure. So it's going to have columns. It's going to have beams. Let's say it's a frame structure. So there's going to be some columns. There's going to be some beams here and there. Okay, now these columns and beams, the structural members have to have the ability to take the load of the structure, to withstand the wind, to withstand the earthquake. And once you have made so that they can withstand all of this forces, the wind force, the earthquake force, the self weight, and all of those forces, then your design is complete. So how do you know that they can withstand all of these things? You know it by doing analysis. So that is how analysis and design are interconnected. Now let's go over the thing a little bit more briefly. Let's say that your plan has arrived. Your plan for the building has arrived, and now let's say that this plan is for a residential building. Okay, and we also have another plan which is for a commercial building. So what happens is that the first input is the applied loads. So the applied loads for the residential buildings according to building codes of different countries is going to be different, but it's always going to be different than commercial buildings, because in residential buildings, let's say you're not accounting an apartment to carry more than 50 people at once every day, every single second after it has been built, right? You're not going to be accounting for that. In an apartment, you're going to account that it's going to be somewhere below 50. I'm just saying it as an example. But for a commercial building, you're going to account that there's going to be more than 100 people on a particular floor every day. So you have to account for that kind of load. So residential building is actually being counted for lesser load than a commercial building. So that's the applied load. And then we have material properties and geometry, which also actually play a role in the applied loads. For example, let's say that for the material properties, you can choose different kind of materials, but let's say that we're going to be considering concrete material. So let's say you have 20 megapascal concrete. So you have a 20 MPa capacity concrete, and then for the geometry, let's say that you have a beam here which is 12 by 15, and of the same material properties, you have another beam which is going to be 15 by 20. So let's say, let's consider for the residential building. So if you're considering for the residential building, the beams both have the same material properties, but the capacity of carrying weight is going to be different for both of the beams, right? Because this beam actually has more concrete area in it, and this beam has less, and then the dimensions also play a great role in the carrying capacity. So by the dimensions, we can call all the dimensions all together, and the orientation of the dimensions as well all together, the geometry, right? So that's what the geometry here is acting as another input. So these are the inputs that the material property and the geometry has to have the capacity to carry the applied loads. So that's the condition that we set out with. Now that you know what the capacity should be, let's say the capacity should be 50 kips, okay, kilopounds. 50 kips, and your material property is 20 megapascals, and then this is your section. So we're starting off with that. Now we do the analysis and we get the outputs. So the outputs are coming out to be internal forces, and sometimes people would like to call these internal feelings as well. Why feelings is because let's say that a building structure or any structure can feel like a human body, right? So let's say that as a human, I can feel pain when I'm carrying something for a long period of time. Let's say I'm carrying something on my head. So after a while, I'm going to feel a fatigue. I'm going to feel a stress. So building structures or any structures are no different as well. So these structures are going to feel some stresses and some fatigue. So those stresses and fatigues can be calculated in terms of forces. So these forces, we're calling them internal forces. Okay, so once you put the input in analysis and do the analysis, you get the output. So the outputs are in terms of axial force, shear force, bending moment, torsion. And now this is not true for all cases. Let's say that for the building structure or the beam, we are going to get shear force, bending moment, and maybe torsion, but not axial force. And there can be some little axial force. But let's say if it was a column, then we're going to get axial force, shear force, bending moment, and maybe torsion. But what if it was a truss? Let's say if it was a truss or a truss member, in that case, that truss member will not feel any shear force. There's going to be no bending moment. There's going to be no torsion. There's only going to be axial force. Okay. All right. So we're saying that, for example. So this is not true that all of these forces must be there, but these are the forces that we're going to be accounting for the capacity. So let's say you did the analysis and then you got all these forces, and then you see that you need this particular structural member to carry 50 kips, but after the analysis you see that it can carry 40 kips. Okay, it can carry 40 kips. That means it is not meeting the requirement, right? So it has a lesser capacity than what is required. So in that case, this internal forces, the output of analysis, becomes the input of your design, because you want a section that can carry 50 kips, and this particular section cannot carry it. So you have to design it, or you can say you have to redesign it, because the geometry is already there, the material property is already there. So this can be called a design, but this design is not adequate for our requirements. Okay, so we have to do a redesign, or we have to do a design. So in that case, I say that I'm keeping the material property, the concrete strength as 20 MPa, but I'm changing the section dimension, I'm changing the section geometry. And let's say this time I am going with this geometry. Okay, now how do I know that if this geometry is going to be able to take the 50 kips or not, right? So what do I have to do? I have to do analysis again. So that is why the output of our design is going to be the input of our analysis. Okay, because this time the applied load may have remained the same, but the material properties and geometry may have changed, or material properties, in our case, material property has remained the same, but the geometry right now has changed. So we have to do another analysis to see the new forces and the new force capacity. And if the force capacity matches this force capacity, then we can say our design is complete, and then we have the final output, the final geometry, the final size, the final configuration. Well, I put in rebar number here because of RC structures. We're going to be mainly talking about RC structures. That's why rebar number is here. But if you are working with steel or anything else, that's why there's also size mentioned as well. Let's see. Okay. So let's say we have analyzed this now. So after analysis, we're seeing that this has a capacity of, let's say, 60 kips. 60 kips, which is greater than 50 kips. So now you have to know that since it is going up the capacity required, is it okay to go with this, or should you bring it down to somewhere near the 50 kips, let's say 52, 51 or 15. So this will depend on your economic perspective as well as safety perspective. Let's say you don't want to do, you need a 50 kip requirement, so you don't want to do a 50 kip exact. Let's say the capacity is going to be 50 kip, the requirement is 50 kip, so that's cutting it a bit close, right? What if some accident happens and you thought that you need 50 kips, but in actuality you actually needed 51 or 52 kips. So that's why we can keep a factor of safety, but let's say that the capacity of this particular section has now become 500 kips. So that's just overkill, right? So 40 kips is less, but let's say 500 kips and the requirement is 50 kips, so that's just overkill. You don't need to spend that much money behind it, right? You just need something that's near 50 kips. In that case, you have to do a redesign again. So you have to put the output of the design in the machine. Let's call this a loop, not a machine. In this loop, and then you have to analyze again, get the outputs again, and do a redesign again. Okay, so let's say that since we got 60 kip from this section, we're going to keep that 60 kip. We're happy with the 60 kip. It's economic and it's also meeting our requirements. In that case, we can say that our design is done and this is the final output. But if we're not happy with it, we would have gone back to the process of this output and then analysis. Now, another question that may pop up into your head, that is, in terms of capacity, you're saying 50 kips or this much force or this much load, which I understand in terms of applied loads, but how do you understand that this section can take 40 kips or this section can take 60 kips? How do you understand that on basis of these? These are not giving you an load number, right? These are giving you force numbers, the axial force, shear force, bending moment. So let's say that you have applied loads. Let's say that load applied is going to be 10 kips, right? So when you analyze the material properties of the geometry for the 10 kips applied load, you're going to get an output, some value of shear force, some value of bending moment, some value of axial force, some value of torsion. And you're going to look for the failure. So if you apply 10 kip loads, does your structural member fail in any of these forces? Let's say that after you apply, let's say this is a beam, you're applying 10 kips to the beam. Okay. And this beam is capable of taking the axial force that is being generated by the 10 kips. It is able to take the shear force that is being generated by 10 kips, but it's not being able to take in the bending moment that is being generated by this 10 kips. In that case, you know that this beam's capacity of the current material property and the current geometry is not of 10 kips. Okay, so that is how you know the capacity and how you match it. Now you're going to understand all of this, and this is going to become more clear, okay, later on. But for now, I just wanted to know the phases in structural analysis and design a bit better before we begin. Okay, so yeah, that was it for this video. Thank you very much for watching.